Have today Irene Amado. She's going to tell us about holographic two-component superfluids. So,
Okay, so is it working? I hope so. So I will, good morning everybody. I would like to start by thanking the organizers first for inviting me to this program and second for giving me the opportunity to speak. I'm a bit sick, so if you want to make comments or questions, they are welcome, but speak loud because otherwise I will not hear it. So I will tell you a bit about some works I've been doing in collaboration with people from Trieste, Madrid, and La Plata in the last year, in which we study some of the features of a holographic model of a two-component superfluid, S-wave superfluid. Here, two-component refers to the fact that the superfluid component itself can be split in two, because there will be two notions of charge density besides the normal component. So it's the normal component, the superfluid component, and this one has two charge densities. Okay, so the original motivation for looking to this kind of multi-component superfluids is the fact that it's known since the 70s from condensed matter studies that this kind of superfluids have unusual Goldstone bosons in the spectrum. And unusual is just because they have a nonlinear dispersion relation, as opposed to what we are more used to, that would be a linear dispersion relation for a Goldstone boson. We wanted to make a holographic realization of this kind of modes and see what we can extract from holography for these models. And we found some interesting questions on the way and also some surprises. The most important thing for me, at least, is that the fact of having a Goldstone that has a nonlinear dispersion relation is a bit in tension with the Landau criterion for stability of superfluids that actually states that superfluids cannot flow with a velocity that is bigger than some maximum velocity, because then they will be unstable towards creating particles. Then you will destroy your condensate, and then you will run out of superfluid. And if you have a Goldstone boson with a non-linear dispersion relation, in some sense it will imply that the sound velocity is 0 for this model, and this will tell you that the maximum velocity is also 0. So you cannot make it flow, so it's not really a superfluid. So we were a bit concerned about that, and we revisited the stability of superfluids. And since this multi-component model that we have contains also the holographic S-wave superconductor, it also gave us some information about the abelian case. Another thing that we found that we were not expecting were some mixed phases where there are more than one order parameter on. We were not expecting it because we were looking just for an S-wave superconductor, and it turned out that when you lower the temperature, even if a priori we had not switched on anything that would break rotational symmetry, the system prefers to switch on some vector condensate. And since the S-wave condensate doesn't disappear, we get a mixed phase in which we have an S and an S plus P wave superconductor. We studied this, it appeared this morning, so you can have a look. It turns out that these phases also exist in unbalanced superconductors that will have, that I will explain later, that have two chemical potentials and lots of charges and so on. And the last thing that we found, that I will not really tell you much about it because it's still very preliminary, is that the abelian S-wave superfluid might have some striped phases that we were not expecting to find there, because they are actually in an intermediate regime of temperatures and velocities. Okay, so since the original motivation we are looking for unusual Goldstones, let's start by telling a bit about Goldstone theorems for general cases. I will show you what is the model, what is the spectrum, how these Goldstones are realized, and what are the features, and then I will switch on superfluid velocity and see what the Landau criterion can tell us about the stability of the system. Then I will change a little bit gears and tell you a bit about computing order in unbalanced mixtures, and let's conclude, wrap up. Okay. So everybody knows what a Goldstone boson is in this audience, and it's nothing but a gapless excitation in the sense that its energy goes to zero as the momentum goes to zero, and they are known to appear when continuous global symmetry is broken spontaneously. But the Goldstone theorem doesn't say anything about how many Goldstones you will find or what the precise dispersion relation will be. If you have Lorentz invariance, then you can actually prove that the dispersion relation is going to be linear, and that the number of Goldstone bosons that you find is equal to the number of broken generators that you have. But if you don't have Lorentz symmetry, either because you are in a state that has, for instance, finite chemical potential, or because you don't have it in principle because you are in a non-relativistic system, or you have some other kind of scaling symmetry, then more general situations can happen, and you can have modes with nonlinear dispersion relation. This is actually what it happens. And then you can classify them in what is called type 1 and type 2, depending on whether they have an odd dispersion relation or an even one. Doing so, the counting of Goldstones gets a bit modified. In the 70s, Chad and Nielsen work out some bound on the number of Goldstones, so the number of type 1 plus twice the number of type 2 has to be greater than the number of broken generators. And it wasn't until last year that there was a proof of what is the actual counting of Goldstone in a general situation. And if you have that your broken the expectation value of the commutator of your broken generators is given by some matrix B, then the total number of Goldstones is just the number of broken generators minus 1/2 the rank of this matrix. And therefore, the total number of Goldstones doesn't depend only on the number of broken generators, but also on the pattern of symmetry breaking. So depending on which ones you are breaking, you can get a different number of Goldstones. This is actually a very general proof. Earlier this year, these people and also some other groups showed that whenever you have a type 2 Goldstone in the spectrum, you will also have some companion that they call massive Goldstone that has universal properties, in the sense that the gap is protected against quantum corrections, and it's completely predictable from the symmetries of the system. So if you have that the parameter that dials the symmetry breaking is the chemical potential, for instance, and the energy will be proportional to it, and this is just the charge of the operator that condenses. So can we construct some model that has both of these kind of Goldstones, for instance? And the answer is yes. And
do you have an intuition why you can have a number of Goldstone bosons that's different from the number of symmetries that has been broken?
You can have that a couple of different directions combine into a unique flat direction.
Yeah, it's typically associated with semi-direct groups. The famous example is you have a crystal, right, and it breaks translations and rotations. And the number of Goldstone bosons is equal to the number of phonons, right? It's only looking at the translations, and the rotations are hidden within that rank B, say, right? That is correct. Where simple groups just happen, right? You need to have some interesting
Okay. So a very simple example is just this linear sigma model in which you have a non-abelian global symmetry. And it was used, for instance, by Dan, Son, and some collaborators to study K on condensation in QCD. But okay, the Lagrangian is just given by this, where you have some chemical potential, some scalar doublet that has some mass and some potential, and it's trivial to prove that there is going to be some spontaneous symmetry breaking of the U2 symmetry down to a U1 whenever the chemical potential is larger than the mass, and then your scalar field gets some expectation value and studying fluctuations around this background and diagonalizing the action, you will find the spectrum, and it will contain one mode that has an energy that is proportional to the momentum, so what we have called type 1 Goldstone, but also a mode that has a quadratic dispersion relation, that is what we call the type 2 Goldstone, and according to this last theorem, it should come with some partner. This is massive Goldstone that has some universal gap. Here, well, the 2 is just because in this model the charge is 2.
You go to your zero chemical potential, then you get what you expect, right? The single,
Yeah.
the usual Gaussian boson, but because you have an I in the exit.
Yeah.
Right?
Yeah, because it is
Okay.
in Lorentz. Yeah.
So it's very basically like you don't have the cleaning action is not real, right?
Yeah.
Yeah.
Okay. So we want to have some some holographic description of this, and then we know that the correspondence tells us that in order to have a global U2 on the boundary, we need to have some U2 gauge symmetry in the bulk, so we will need to have some U2 gauge field. We want still to have some scalar condensate, and then we put some scalar doublets in the game. If we want the symmetry to break spontaneously in the same pattern, so from a U2 down to a U1, the only sourced gauge field can be the diagonal U1, so U2. This is enough in order to have chemical potential that will be given by the boundary value of the time component of this over U1. And if we want also to include some superfluid velocity of in the boundary theory, we just have to switch on some spatial gauge field that gets some finite value in the boundary. The simplest model that includes all these ingredients would just be a U2 generalization of the original proposal by Arnold, Herzog, and Horowitz, in which the U1 becomes a U2 and the charged scalar is now a doublet. And just for economy, we will not consider back reaction, because since we are interested in Gaussian bosons that appear at the phase transition, and we don't, a priori we didn't want to go to very low temperatures, it's enough. So these fields will be living in an ADS for black hole background. Just mentioned that Gaussian bosons of the boundary theory will correspond to quasi-normal modes in the bulk, of fields in the bulk. Here's the Lagrangian of our model. These are just the generators of the symmetry. If you do, as I said, and you search only the overall, the diagonal U1 of the symmetry, of the gauge symmetry, and you give and you allow for finite chemical potential velocity, it turns out that the background of this theory is precisely that of the holographic abelian superfluid with finite velocity that was studied by Elsa, Kaufman, and so on. But for one thing, here we have that the symmetry breaking is from a U2 down to a U1, and the scalar field acquires a depth. But furthermore, there is another component of the gauge field that gets a depth. Is the other U1 inside the SU2 gets some expectation value, and then you will have two charge densities, therefore two charged currents on the boundary, and that's why this model is a holographic realization of a two-component superfluid, even though we have only one chemical potential in the game.
X.
It's the boundary value of the gauge field, of the spatial gauge field on the boundary. So the boundary value of the gauge field. Yeah. Yeah. So it's related to the sound velocity, to the field velocity, superfluid velocities. Okay. So yeah, so it's a two-component superfluid. That's why, in this sense, it gets that name. We can look for what are the fluctuations of the system in the normal.
I'm slightly confused. You say it's a two-component superfluid, right? When I would kind of claim there's a coexistence of a metal in a superfluid. Does that make sense? Right, so if it's unbroken U1 subgroup, right?
Is what?
There's this unbroken U1 subgroup.
You will have that both of them are superconducting, actually, both components. Even though one is not allowed to flow.
Perhaps you continue.
Yeah. So yeah, in the normal phase, the scalar field is trivial, and the fluctuations, if you follow the lowest quasi-normal mode, when you lower the temperature, it will eventually become tachyonic, simulating the change of phase, the creation of the condensate.
What is the meaning of the different colors?
It's different modes. It's like the first and the second.
Second and third.
Yeah. So the lowest one is the one that becomes tachyonic first, finally in the phase transition. And since now we have a doublet scalar, we have two copies of this spectrum, and we also have 4 diffusion modes whose dispersion relation is given by this form. With this, the diffusion constant, and it just corresponds to diffusion of a normal charged fluid. In the broken phase at low temperature, we will generate some condensate of the scalar field that you can compute as a function of the temperature for different values of the velocity, from 0 superfluid velocity to some value I don't remember, but large.
Y-axis.
Sorry?
What do you plot on the y-axis?
Oh, here is the condensate,
Yep.
normalized by the temperature, and here's the temperature.
We have an, that's called the emergence
Metastable.
Oh, yeah, here, yes.
Yeah, right? So
Yeah,
at
yeah.
low temperature.
So if you compute the free energy, yeah. So if you compute the free energy and you compare it with the normal phase, what you will find is that there is a second order phase transition as far as the velocity is small, and then it will become first order as you see from the condensate. This is precisely what these people also found. So as I said, the background is the same, but if you look to the fluctuations, they will decouple in three sectors. One is the preserved U1 that survives the spontaneous symmetry breaking, and then there is the abelian sector that actually corresponds to the U1 as wave superconductor, and there is also a non-abelian sector that contains the type 2 Goldstone, and each of them is related to one of these two charge densities that I was talking about, so that's why you have two components. Since the abelian superconductor is a subsector of our system, the two-component superfluid will still give us information about it, so whenever I talk about the abelian sector, you can also extrapolate and talk about just the abelian superconductor or superfluid. So let's look to the fluctuations in the broken phase, and in the abelian sector we find, as we should have expected, some type 1 Goldstone boson that has some linear dispersion relation, and that can be identified with the fourth sound of the superfluid. Fourth, because we are in the decoupling limit in which the normal component is not allowed to flow. If we had allowed to flow it, it would be the second sound. But the important thing is that there is a linear piece, that is where the coefficient is to be interpreted as the sound velocity in the superfluid, and it's plotted here as a function of the temperature. And here you have the attenuation gamma as a function of the temperature, and also as expected it goes to 0 when the temperature is small, because the system becomes more and more ideal. In the non-abelian sector, what we find is a Goldstone boson that doesn't have a linear term. It has some quadratic dispersion relation, and therefore we identify with the type 2 Goldstone. Okay, so attenuation goes to 0 much faster, and this is the real part coefficient, and you see an extra peak that is actually signaling the instability to these mixed phases that I was talking about at the beginning. And at around 4.4, there's going to be a P wave forming, some vector condensate, and the low temperature phase will be an S plus P wave. I will tell you about it later. But the important thing about this mode is that this doesn't have a linear term. You can also look for in the massive companion, and we found a mode that in the broken phase, this is in the normal phase, in the broken phase has some linear gap with the chemical potential, as we would have expected. In this case, in our particular notation, the charge is 1, and it actually is linear. Okay, we can also look for what happens to the diffusion modes.
I mean, this would mean that the modes of that.
Sorry?
That, yeah.
Yeah, so I look at the numbers on the y-axis, and I find out that the imaginary part is actually larger than the real part. So it's
Yeah. Okay, so diffusion.
Yeah.
So the diffusion mode has to, since the hydrodynamic regime will be dominated by the Goldstones in the broken phase, the diffusion mode has to drop out of the hydro regime, and this actually means that it has to develop a gap in the broken phase. It's the cheapest thing that it can do, And it's actually what it does. It develops an imaginary part that is temperature dependent. It grows with temperature, and eventually, at some temperature, it will be overcome by some other normal, quasi-normal mode, some higher mode. And if you study the response, what you will see is that there's going to be some crossover between an exponential decay of the response, in the case that the lowest mode is this diffusion mode, versus a damped oscillation when this is the mode with the lowest imaginary part. And it has been studied for out of equilibrium processes in quenched superfluids by Bashin and collaborators, and this is actually what they find. But this is actually not a general thing, because if you look to the non-abelian sector, where there are actually two diffusion modes, what they do in order to get out of the hydrodynamic regime is to merge and develop some real parts. So they get off the imaginary axis and develop some real parts. So no qualitative difference in the response will be seen. So that's the spectrum of the lowest lying excitations of the spectrum. And what we were a bit worried about is this fact. Because as I said, it's in tension with the Landau criterion, and the reason is the following. So the Landau criterion is just established that if you have a superfluid and you make it flow, it can do it with a velocity that is bounded from above. If you try to push it faster, you will start creating particles for free, you will break all your condensate, and then you will run out of superfluid. At zero temperature.
The criterion has a very bad reputation in condensed matter.
What?
It has a very bad reputation in condensed matter. Right, so the better question to ask is when you push too hard at some point, vorticity explodes.
Okay.
Right, and it's not particles. It was like a 1960s idea.
Yeah.
Right. So it's basically like hydrodynamical.
Well,
So
but it will not
superfluid
be.
hydrodynamics just means that you have irrotational flow.
Okay.
Right, and
But anyway,
as
you
long
will
as
change
you protect the
phase.
irrotational nature of the flow, you will find, but when you overcome the mass gap associated with rotations, then
But anyway, you
and it all
will.
boils down to the same criterion to decide.
Yeah, but with this type of model that she's
with that-
interested, is this is the right way to do it?
Because the vortices will not appear
Yeah,
here.
but
But
you don't have vortices.
in a real one, yeah, that's true. But here you will
Yeah.
not.
I think Landau criteria is just nonsense.
No. I mean, the Landau criteria is nonsense if you don't
Landau
have
hadn't quite
vortices.
understood symmetry breaking at that point in time.
But there is a Roton minimum which is effectively
Exactly.
Exactly.
significant.
Yeah.
It's more
But-
important than just
Yeah.
phonons.
And the other question is like, I'm kind of confused, right? So I tend to read it as you have your S wave, and there's really the superfluid. And then you have your non-abelian part, and I see that there's kind of internal symmetry. Right? You have somehow a condensate, there's an extra internal freedom. Now, it occurs to me that you have to ask two different questions. One question is just a plain superflow, which is like an S wave.
Yeah.
And then there is the internal degree of freedom, which is fragile, right? And
Is what?
fragile, right? Because you have a quadratic dispersion, it's easy to destroy. But what does it mean physically? When you just apply pressure to this stuff in a vessel, perhaps you don't talk with that internal non-abelian mode.
But you cannot do it because it will become unstable.
To what?
Well, that you have to that you have to think about.
In reality, also the fluids are stable significantly lower at this criterion, Landau criterion,
Yeah.
even below.
Yeah, but in this-
it has to do
Because
in
of the
with the
walls,
nature
yeah.
of the
But in
symmetry
this
you are breaking.
particular case, the
Wait. It has to do with the nature of the symmetry you're breaking. The S wave is the S wave, and it's in charge of the mass transport, and that is superflow. There is extra mode that is fragile, is unrelated to the mass flow, it's some other flow. What the heck is that flow? That's the
it cannot
question.
flow. That's what we find.
Yeah, this is the prediction that.
It cannot flow.
The mass can flow because you have
The mass can do it, but
Yeah.
but the other part
There's other
cannot.
thing that can flow. What is it?
No, it cannot.
I ask not whether it cannot flow, I ask what it is.
that I don't know. You should try to find it.
That's
My
the
guess
point.
is that it will be some striped thing, but
We have to
yeah.
see that as the interpretation issue, I guess.
So, for instance, in the case, you will see. So, yeah, so even if it is not a very loved criterion, let's keep it for now. So, at 0 temperature, you can show by using Galilean invariance that this maximum velocity will be given by this minimum of the energy over the momentum, where you have to take the minimum over all the excitations in the game. At final temperature, you don't get something that nice or easy, because first of all, the energy will depend also on the temperature. But you can rephrase this thing into the following statement, that is, you will have an unstable flow whenever all your excitations have a positive energy. And if you only had phonons, this would imply that the flow is stable if the sound velocity in all propagation directions is positive. Of course, you could have quantum modes, you could have rotons, you could have many things, but if besides all of those, the lowest excitations will be the Goldstones. And for the Goldstones, by using these things, if you have a nonlinear dispersion relation, the prediction is that the maximum velocity at which the superflow can flow is actually 0. This is our case. In our holographic model, we only have, in this model, we only have Goldstones that are given by quasi-normal modes, and stability implies that for the flow to be stable, the real part of the quasi-normal modes has to remain positive, and the imaginary part negative. Actually, if you had an imaginary part that is positive, you will have some mode that is exponentially growing, so of course it would be unstable. As I said, naively, from what we found at 0 velocity, at 0 superfluid velocity, we found a type 2 Goldstone whose dispersion relation is quadratic, and according to what I said, it will imply that this is 0. So if we want to try what happens when we switch on some velocity, in the non-abelian sector, we have to look for the instability that we expect to have. But in the abelian sector, in this with component, what you have to look is for, you have to compute the sound velocity depending on the direction of propagation with respect to the propagation of the flow, and the maximum velocity in that case would be given by the velocity at which the superfluid velocity at which the sound velocity vanishes. So let's do that. And in the abelian sector, the type 1 Goldstone looks like that. Here you have the sound velocity as a function of the angle between the propagation of the flow, that is to the right, and the propagation of the sound. And here you have the attenuation. From blue to green, the velocity of the superfluid is growing, and you can see that at some point the sound velocity vanishes. At the same value of the superfluid velocity, so does the attenuation, so they vanish simultaneously. And if you try to make it move faster, this will become negative and this will become positive. Just for fun, don't kill me for that, we found Andreas Schmidt sent Karl and Steiner a plot of some results that they found for a weak coupling model of a S-wave superfluid, and it looks pretty similar, even though I don't want to make any claim about it, but it's nice that it resembles a weak coupling computation. So, as I said, if you try to make it flow with a velocity larger than some value for each temperature, you will find that the velocity becomes negative and the attenuation positive, and then you will have some instability on the system, and you can check it by looking to the dispersion relation of that mode. And this is what we have here, is from blue to red velocity growth, superfluid velocity growth, and for some particular value it becomes negative, the real part of the type 1 Goldstone, whereas the imaginary part becomes positive, signaling an instability, as we would expect. But we can say more, because since the instability takes place for a finite value, for a finite range of the momentum, and the maximum of the instability is at finite momentum, we should take this as a hint of a striped phase, or of instability towards some modulated phase in the superfluid.
This is more in helium. It happens crystallization of the film.
Yeah.
It just helium atom crystallize on the surface instead of superfluidity.
So it is driven, right? So you basically push the superfluid,
Yeah.
and when the velocity gets too high, then it becomes unstable, everything's all fine.
Yeah.
And then you suspect that then you have sort of a
That
spontaneous
you will have some
formation
modulation.
of a
Yeah.
modulated current.
Yeah.
Superfluid density is like a modulated, right?
Yeah.
But it's different from helium. It's not just
You need,
focused with
yeah, you need
static crystal.
extra contribution into that, to that stripes, that extra something.
It's really driven
Yeah.
instability, right? Like a pattern formation.
So it's
more
like
than
binary
a,
instability or something.
play competition between crystallization and superfluidity in helium.
Yeah.
Interesting. I haven't quite seen this before
Anyway.
in anything existing in the superfluid world.
Uh,
there anything,
striped
you
faces
know?
in a real superfluid?
Yeah.
No?
Stripe faces
Yeah.
in quantum Hall effect.
Again, when you drive helium and you go too fast, it just turns into normal liquid.
Okay, but this.
Right? It won't break translation.
But in that case, you have also other modes. Again, you have rotons, for instance, that here you cannot have. So this is a toy model. In this particular case, what you would find is
Yeah, but it might be that if the frequency is small enough, there is a region in which is below the first roton, so you might see it. So
that
it's
could be.
not
Yeah.
it's toy, but
Yeah.
It could be, it's an interesting dynamical pattern formation.
So, okay, so we spent some stripes, and we are trying to construct solutions. We have some preliminary results.
Why aren't these just waves?
What?
Standing wave?
Oh, it could also be, but we looked for inhomogeneous solutions, and we found some examples. So that's why stripes are more likely to be just by experimental.
And again, it's not the density of the fluid, but it's the currents, right?
Is it what?
The
The
currents
Yeah.
doing it. Right, so yeah, that's sort of a pattern of currents
Mm-hmm.
that then break translations, right? That's this statement.
Yeah.
Yeah. Right, and somehow there is vorticity, there's likely circulation
No,
somehow.
there is no vortex.
There is no, it's a single
It's a
momentum type thing.
constant. Yeah.
Can you be sure that there are not more momenta involved? So when you imagine that it's like a checkerboard
Mm-hmm.
that's forming, then you expect that there is circulation all over the place.
But
Right, so you have fast moving stuff, slow moving stuff forms a translational pattern. That means that things go around.
that makes
no, but I think
This is
different.
not a density
Yeah.
instability, this is a flow instability. Right?
yeah, you are.
Yeah, so when you have flow instabilities, there's immediately the question whether that involves a circulation in the flow, and ask you whether you have looked at it.
No, but
No, you
Comparison is
didn't.
because
No, no,
look at
standard
it.
conventional hydrodynamic Helmholtz instability. How are they related?
But
Helmholtz
it's,
is-
no, it's
But
a real,
that-
real dynamical pattern.
She's talking
information
about
thing.
something else. You're
Yeah, this is
insisting
dynamical,
on
yeah.
vorticity,
Yeah.
on things like that, but she's talking
But
about
here-
something
No,
else.
no,
which
no,
you may
I
like
just,
to know,
and
but-
excuse me, gentlemen, you're thinking that this is a density instability. It's not. It's a flow instability. And flow instabilities occur, right? In hydrodynamics, you
1D,
have a
this is
beautiful,
1D.
you know, the sun and so forth. It's something of that kind.
It's Helmholtz
And now you have to ask a question, when that thing has a spatial periodicity, right? You expect immediately that there's somehow in that flow circulation.
But I mean, it's,
Like in normal hydrodynamics, when you look at the what's called
I mean, there is no such something
effective
here.
roles.
Let's Irene continue.
What do you think?
I'm the chair. Let's.
Well, Tony, what are you reading there?
No, what
This
I'm
is about
saying.
interpretation.
No, it's she's talking about something else. You're insisting in vorticity.
No,
let me
what
see
is she talking about, Antonio?
Hmm?
What is she talking about?
she's talking about in another type of instability. It's linear, so you don't have it's something different, right?
Yeah,
Ask whether there are two wave factors
so
out
maybe
there and the
we
sequence
can-
well,
can.
there is just one vector. There is just one vector. It's,
Yeah.
it's the velocity. It's a flow in one
Yeah,
direction.
it's
You are just trying to
dimensional.
push all the flow together.
Right, and then it's faster and it's slow and it's faster in one direction.
in one direction.
It's homogeneous.
But now I ask, what about two directions? How can you-
But we haven't done that. We have done just one direction.
Okay, let's continue.
Okay.
So this is an x-axis is absolute value of k.
Yes.
So for any direction.
For any direction, you will find that, but you find it before in the backwards propagation. So the instability appears when you try when the sound propagates in the opposite direction to the flow. It's where because you have this asymmetry between forward and backward propagation, so it appears before in the opposite direction. But if you keep on increasing the velocity, you will find instability in any direction.
What is component here on this picture? What is VS? What does the component means? VS and VS or?
Oh, this is just the value of the sound velocity depending on the direction with respect to the superfluid flow that is going to the right, and then you can propagate in different with a different angle with respect to the superflow, and you compute the sound velocity, and this is what is plotted. For each curve corresponds to a fixed fluid velocity, and all the curves are for the same temperature. Okay.
Do you know what is the mechanism of this?
Definition? You mean
I've seen it this kind of spectrum.
why?
In fermions, but not in bosons.
Yeah, it was unexpected. Yeah. I think it's because because this happens also only in the abelian sector. Because I was going to say something stupid, but yeah, it seems that when you have large enough velocity, you are just breaking invariance, and then
What is velocity here? Because
each curve is one different velocity. It grows from blue to red. So when it's big enough that you cannot make all the superfluid move together, and then you will. That's why I expect to create some stripe faces.
What is changing along these different curves?
So this is some value of the velocity, and then it grows when you go from blue to red. So if you are at small enough velocity, the fluctuations are stable, but above some limiting value, you will get some instability.
But it's morally quite similar as to the way that you find out instabilities in normal dynamics. I think you want to discover within the regime with effective flows. You do pretty much the same linear stability analysis. Some kind of zero temperature generalization.
Well, this is final
Yeah.
temperature. But,
Yeah, but it doesn't matter, right? It's superflow generalization.
Okay, but if you look to the other sector that you were concerned about, the non-abelian one, what you find is that it's unstable no matter what the superfluid velocity is. So it cannot flow. You cannot make it flow, this component. For every temperature at which the S-wave solution exists, whenever you try to switch on a velocity, no matter how small it is, you will get that the system is unstable. Okay.
Right, so this is an overall velocity. Right?
Yeah.
They're still struggling to try to understand
Yeah.
what is second symmetry.
So this second symmetry is telling you that you cannot make it move.
Yeah.
It's not. It doesn't flow. It's actually unstable. I don't know towards what. Probably also some kind of inhomogeneous phase. But But if you look at the conductivity, you will see that there is a delta function in the DC conductivity, so it's still a superconductor.
You can also have a fault.
Yeah.
Okay, so it's illustrate. So you have the
Well,
normal S-wave also sector say that the mass transport is doing the normal job. And now there's this internal symmetry type thing that's saying somehow when I move the condensate, it automatically
prevents from moving.
dissipates.
Yeah,
in
it
the
prevents
second
from
mode.
moving.
Insane.
A question? Does this mean there's a tachyon in the
Yes.
Yeah. Okay.
Yeah, because the imaginary part is positive.
So, but is it related to the mode that you showed earlier, or is it?
To which one?
You showed a bunch of Goldstone modes with imaginary part.
Oh, these are the Goldstone bosons that they appear in the broken phase when you create a condensate,
Right.
and they are perfectly stable at 0 velocity.
Okay.
But when you switch on a superfluid velocity, they become tachyonic. So there you have some instability. There should be some other phase.
I see, but an arbitrarily small velocity does.
Yeah, for this type 2 Goldstone, it's arbitrarily small.
Okay, but that doesn't mean there's a tachyon, a perturbative tachyon about the phase itself. Is that right?
No.
It sounds a bit like that you want to again do some kind of pattern formation in the flow, right? This is not necessarily saying that there's no dissipation flow, but it's saying you just have to push it that somehow the second symmetry sector also organizes itself in an interesting spatial pattern.
Yeah.
That is,
Kind of.
yeah, it's very interesting.
Question? So in the type 1 case, do you know how the position of K where this band become minimum dispersed with scale with the velocity?
It's a person
So in the previous paragraph,
Yeah.
how the position of the K where the minimum occurs, how does that depend on velocity?
No, it actually gets.
The real part.
Real part.
Oh, this one.
Yeah.
No, I think we have a plot, but I don't remember. I don't think that there was a clear scaling or anything.
So the first mode that become unstable is finite K. So as you
Can you speak a bit louder because?
as velocity increases,
Yes.
there is some critical velocity at which this.
At which it becomes.
Yeah.
The thing is that it becomes unstable at 0 momentum.
Oh, I see.
So it just starts to develop at 0 momentum. Then, of course, when you go to larger velocity, you have more region of momentum in which it is unstable, and then the minimum it's at some finite value of the momentum. But when the phase becomes unstable, it's at 0 K. So it's different to the usual picture of striped phases where you have that this will happen like this, no? Like between 2 finite values. In this case, it just starts at 0.
I've seen
this
precisely the same pictures for Couget flow, right?
really?
Yeah.
Okay, then you
No
have to show me.
dynamics.
Okay. So putting it together in a phase diagram for the abelian superfluid, according to what this criterion would have to tell us, you find that the temperature at which the S wave becomes unstable and ceases to exist is actually lower than what the free energy would predict. And then you have S wave superfluid for low temperatures and bounded for some critical, for some maximum values of the velocity, and then for large enough temperature you get the normal phase, and in between, because of these finite momentum instabilities, we would expect to have some stripes, but this of course has to be proven that they are there or what happens. But for the
Can I ask a question about, just out of my curiosity, it's not a problem that one slide back, that the minimum, just even at 0 fluid velocity, that the minimum of the dispersion relation.
no, it's not the 0 velocity is not plotted. The 0 velocity is perfectly nice.
Okay, 0 velocity, no.
Yeah.
Okay.
No, at 0 velocity is stable otherwise. For the 2 component superfluid, once you include the non-abelian sector, we have seen that there are instabilities for any value of the fluid velocity, and then also that it's superconducting but not superfluid in some sense because you cannot make it move But at zero velocity, we had seen that there was another instability that I mentioned when I presented the coefficients of the dispersion relation of the type 2.
Yeah, right. I'm slightly confused with that. You have some direction of a velocity along which you boost the
Yeah.
system. And you have a momentum directions also, which can be any arbitrary directions. And you are saying that this momentum direction is independent of which direction you are boosting.
No, the velocity will depend on the direction of the momentum.
Oh, then here K.
Oh, in the case of the type 2,
Yes.
you mean because here this doesn't
Yes.
happen?
Right.
It's because the type 2 Gaussian boson doesn't have a linear term. It's quadratic, so you don't really have a sound velocity. It doesn't make any sense to make that plot, because it will not depend on the direction for this case. For the type 2 Gaussian, it's completely independent of the direction. For the type 1, it does depend, and that's why this plot is not symmetric. But the type 2 Gaussian doesn't have a linear term, so the sound velocity morally is zero for this one, propagation velocity. Okay. Okay, so yeah, changing topic. At zero velocity, there was another instability at low temperature that we saw as an extra peak on the dispersion relation of the type 2 Gaussian. And you can actually go and look for the fluctuation that becomes unstable. This plot is old, but anyway, it's the same information. And you see that eventually some mode becomes has some imaginary part that is positive, so again becomes tachyonic. You can trace back this mode, and is a gauge field excitation. So you would expect that there is some kind of vector condensate appearing at this temperature. So we looked for the new phase. And what we actually found is that actually that's the case. There is a P wave forming, but there is some component of the non-abelian gauge fields that will get some expectation value. And you will enter a phase with two condensates, because when here is the vector condensate, here is the scalar condensate. Blue is for the S wave phase and red for the new phase. And when the vector condensates start to build up, the scalar condensate doesn't disappear, it actually becomes larger. By looking at the free energy, we saw that this new phase is the preferred one whenever it exists. So that's the phase diagram, sort of. You have an S wave for temperatures between these two values given by these 2 points. And then the symmetry is breaking from U2 down to U1. But if you try to go to temperatures lower than this other temperature that would be given by this point, you also generate a vector condensate, and you have an S plus P wave phase in which all the symmetry is broken, but also special rotations are broken. And this phase will survive only as far as you don't switch on superfluid velocity, as we saw. But the question is like, okay, there is no phase with only a P wave in this system, because the creation of this condensate is completely supported by the fact that we had this other expectation value for another charge density, even if it didn't have a chemical potential. And then without this other chemical potential, no P wave will appear. But we can think that if we switch it on, and then we have really two different chemical potentials for two different charge densities, this S plus P wave could disappear and become just a simple P wave. So we investigated a little bit on unbalanced mixtures that are just that, some systems that have more than one species of charge with some different chemical potentials, like if you have some baryon and some isospin chemical potentials. And these kind of systems usually are present coexistence and competition of different order parameters. They are also usually unstable towards appearance of inhomogeneous and anisotropic phases, but we haven't looked at that. In this case, we get to an unbalanced mixture just by switching on both chemical potentials in the two U1s that live in the E2. And the symmetry group is breaking down to a U1 times U1. And what we found is that all the three phases are now realized, and they compete in some regions of the parameter space. There is a very similar, there are a couple of similar models to this one by Bigazzi and friends, and another one by Johanna and collaborators. In this one, instead of having a U2 symmetry, they start with a U1 cross U1. And in the paper of Johanna's, they don't have a scalar field. And both of them cannot realize this kind of phase, but the other phases that we found are actually in their examples too. Information is encoded in this phase diagram, which you have. This is the chemical potential that we have switched on since the very beginning, and here we have the other one. It's also switched on, and turns out that okay, this is what we had found for the mu equals 3 equals to 0, mu 3 equals to 0, sorry, that you have normal phase, and when you lower the temperature, eventually you will get to some S wave phase, and if you keep on increasing the chemical potential, you get to some S plus P wave phase. By switching on another chemical potential, this phase survives as far as it is not too big, but probably it will disappear at some point. We cannot really go to very small values of what would be the temperature because we didn't include that reaction, but it might disappear. But if you start in the case where this other component of this other chemical potential is very large, what you find is that the system prefers to go first to a P wave phase, and then you will find a first order phase transition to the S wave. And this is because there is a competition between the two chemical potentials for condensing first the scalar or the P wave or the vector mode. In this kind of models, it's expected that there are some inhomogeneous phases close to the quantum critical point, so it would be interesting to look at that in a back-reacted model that goes to very low temperature.
You get here important, right? So this is mystery. What the second Goldstone boson is, and what the meaning of the U1 symmetry direction is. Now, when you break that extra U1 symmetry direction in the S wave, you find out that it gets unstable to an S plus P wave.
Yeah.
Right? So the S wave you can view as a disordered S plus P wave.
Yeah.
I don't know exactly how to look at it. I don't think that you find it in the conventional commensality context. But then somehow you would think that also the Goldstone, the magnetic Goldstone is somehow associated with a symmetry break.
We haven't.
Right, so I guess when you consider the transition of the check from S wave to S plus P wave, I guess you then also find a tectonic instability of the Goldstone.
Yeah, this
right?
is what
And
we
that's
found.
basically telling that somehow.
But it's not the Goldstone that is unstable, it's a vector mode. What
to
is
confuse
unstable.
matters further.
It's another excitation that overcomes the Goldstones and becomes unstable.
So basically think that
So that's why.
the system.
So my expectation is that the pattern of Goldstones in that case is that you get 3 Goldstones in this other phase, because you still have this other 2 and you will have a new one. And I say new because it's not that one of the Goldstones is becoming unstable.
Perhaps to put out some question, whatever. So you find out that when you drive this way, that the magnetic sector goes unstable, it also forms some spatially modulated pattern. And could it be perhaps that the modulation is really in that it figures out sort of domains of S plus P?
Yeah, it could also be that you are actually generating something different, but it didn't look like there is a P wave in that case. I mean, you cannot have a P wave in this wave case because you only have a U1 symmetry, so you cannot break. How do you break?
We have a Goldstone boson when you are vibrating something and on an S wave that is not S wave symmetry. Right, that is the
It's not
with
this
the
way,
type
but
one,
it's
so
not
the type
going to be
two
also a
has an
vector.
internal symmetry thing, it has to be.
But, oh, you mean for... Okay,
Right, and then ask the
no,
question,
I
right,
was
you get
thinking-
this sort of courgette flow patterns
Yeah.
or something, and what is that something?
Yeah, but it's hard
Could
to
it be
look at.
related to
But
the
it's hard to look at
components?
that, so... It's hard to look at that, so we haven't...
You don't know
yeah.
quite yet, right? Yeah.
But, yeah, it could be.
Something of that kind.
Okay, so just let's summarize. So what I show you is that holographic component superfluids can accommodate this kind of unusual gallstones and their partners on all that features expected for this type 2 gallstones. We have also seen that if you study the quasi-normal modes, there's fluctuations even in the abelian superfluid. The phase diagram that we would have guessed for at finite velocity gets modified, and the superfluid velocity at which the S wave ceases to exist is lower than what the free energy would have tell you. I would like to think that there are some hints of a straight phase because of this finite momentum instabilities. We also saw that for the multi-component holographic model, at least, that includes some type 2 gallstone, they cannot flow because they are unstable whenever you switch on a velocity. And we also found some mixed phase at low temperature for an imbalanced superfluid, together with an S phase and a P wave phase. It would be nice to include back reaction and see how the gallstones interact with the other sound modes, like the normal sound, and check for what happens close to quantum critical points and if there are any low phases in this state and imbalance models. If instead of having a scalar field, we would have a pseudo-scalar, it would be interesting to look for this this kind of state that is time that breaks time reversal, and it's typical of a topological superconductor, and it would be nice to be able to realize that holographically. Thank you.
Some additional quick question?
So once you consider the back reaction, what sort of infrared ground state would you expect?
This is the thing is that there should be some kind of inhomogeneous phase, at least, for instance, if you have, just in the case of a P wave, close to the critical point, there would be kind of a window opening of an inhomogeneous phase that in this particular model it would be expectable to find. So yes, I don't know if it's right, but some modulated phase.
What other parameter has this pair wave superfluid OS plus pair wave?
It has both. It has an S wave and a vector.
Can you write what the parameter? What is the symmetry of the parameter?
The scalar field and the scalar field and a component of the non-abelian.
So it's the component of the parameter. Or
yes. Okay. The condensate is the subleading term in the field. Like if you have, okay, so the scalar field, for instance, the scalar field at the boundary, I don't know if you see here. So the scalar field at the boundary, close to the boundary, it will go like, in our case, for the mass that we have, but it can be that the powers are a bit different. Something like that. When R goes to infinity. Using the correspondence, you know that this first term will correspond to a source for the field, whereas this second term will be the expectation value. We want the symmetry to get broken spontaneously, so we set this to 0, so there is no source, and then this psi 2 is basically the expectation value of the scalar field. And how it looks like, I show it.
Yeah, you see what she did in the top.
Yeah, I show it
How do you know
somewhere.
it's pair wave?
Sorry?
How do you know it's pair wave or S plus pair wave?
Well, it's a scalar field. It corresponds to a scalar operator. It has to be some S wave, right?
Right, for S wave, but for P wave.
For the P wave, what you have is instead of the scalar field, you have some spatial component of a gauge field that has also some over R, I think, in this case. Again, we set the source to 0, and you can plot this, that is going to correspond to the expectation value of some current, and it's also what I plotted.
Okay, I think we can continue this discussion later because we're already late. So let's thank Irene again.